Bismillahirrahmanirrahim. Assalamu alaikum. I'm Engineer Misha, Chairperson Community of Research and Development, and I'm going to present my research paper titled as Nanotechnology 45 nm based low power and high performance 4x4 multiplier based on 6 transistors, full adder, and 2T XNOR Gate in IEEE Cube 2021. Among other authors are Engineer Muhammad Zishan, Engineer Osama Gulzar, Muhammad Munir, Zishan Abbasi, and Osama Babar Abbasi. The table of contents are motivation, introduction, literature review, proposed methodology, results, discussion, conclusion, and references. Motivation. In current times, transportable smart gadgets driven by intense computing powerful batteries have been tremendously advanced. With the rise in complexity of ICs, the energy needs of such components have multiplied. Investigators are exploring novel ways to develop low power and high speed circuits with low operational areas to develop realistically feasible, economical digital gadgets. Many approaches have already been presented for performance and power efficiency improvement. Introduction. Today, there is an ever increasing number of portable applications requiring low power and high throughput circuits. Therefore, low power design has become a major design consideration. Common techniques at module level for reducing power consumption are node capacity reduction, event minimization, the voltage swing is lowered. Modern processing systems power consumption is quickly becoming an impediment to the development of integrated circuits. That's why immediate attention is needed to address this problem. Literature review. Authors in one designed a 4x4 multiplier by using 6 full adders, 4 half adders, and 16 AND gates cascaded together. Their full adder contained 8 transistors, half adder had 5T, and XNOR gate had 3 transistors. Two designed their 4x4 multiplier by designing their full adder with newer gate diffusion input GDI transmission gate configuration, which is a combination of single PMOS and NMOS. The multiplier utilized 324 GDI transistors with a delay of 0.035 microsecond. In three high-speed adders are used to develop a 4x4 Vedic multiplier by using a GD technique. The half adder utilized 189 picowatt power with 12.51 nanosecond delay, and full adder 76 picowatt with 40.26 nanosecond delay, which is quite reduced as compared to CMOS technology designed architectures. Authors in 4 designed 4x4 with an adiabatic switching principle. This multiplier utilizes two-phase clocked adiabatic static CMOS logic units. They also added sleep mode transistor logic to improve their results, in which the power supply is basically in standby mode. I proposed an improved 4x4 recursive multiplier architecture by half adder and full adder based on NOR gates with 45 nanometer technology. Researchers in 6 embedded 1-bit adder design with the help of multiplexers. The partial products of this 4x4 multiplier took log 2 of 2n time. The half adder architecture utilized 6 transistors for area reduction. They applied the concept of parallelism to further increase the speed of multiplication steps. Multiplication algorithm. A combinational multiplier is an excellent model that demonstrates that basic logic units, gates, half adders, and full adders can be coupled to create a higher complicated operation. Mathematically, this is how 4x4 multiplication is done as shown in the equations. The first two steps of the multiplier step shows 4-bit multiplicand and a 4-bit multiplier. Step 3 to 6 shows the generation of partial products, and the last step shows the addition of partial products and then a left shift to get an 8-bit final product. Proposed methodology. In this research, we designed a low-power, reduced, real, and fast-speed 4x4 multiplier with the help of architectures which has the minimum number of transistors. Submodules used in this multiplier architecture are 2T-based XNOR gate, 2T AND gate, 4T-based half-adder, and 6T-based full-adder. This figure shows the block diagram of proposed methodology, that is 4x4 multiplier. 2T XNOR gate. This architecture based on a two-transistor circuit needs non-complementary inputs and provides an almost flawless outcome when input combinations are 00, 01, 11. The output signal of the XNOR operation will be accurate. While AB is equal to 10, NMOS is activated and passes the low HI pulse amplitude to the output. Figure part A shows 2T XNOR gate schematic and B shows timing diagram. 2T AND gate. When the X value is 0, the cell line is low. IN1 is chosen to the output because IN1 is grounded. The output is always in the low condition. On the other hand, when X is 1, that is the select line is high. Input 2 is picked, and because Y is linked with input 2, the output will be either low or high depending on the logic level of Y as shown in figure below. 4T half adder. While the above design 2T XNOR and 2T AND gate, one half adder with 4 transistors can be easily designed. The 4T half adder block diagram is shown in below figure. 60 full adder. The entire 60 adder has 3 modules as shown in figure. Here, 2T XNOR gates and a 2T mux. It is possible to obtain the sum and carry using below equations. Because of the desirable characteristics of a relatively small amount of number of transistors and a little 2T delay, it can work with low power consumption at a fast speed. By employing the suggested 2T XNOR gates, the entire adder circuit count, associated power reduction, and delay are minimized. The sum is generated by cascading XNOR of the 3 inputs, and a while XNOR logic is used to obtain the last sum of the products. Results and discussion. The implemented 6 transistor based half adder and 4 transistor based HA don't have immediate linkage to or port, and the likelihood of the straightforward drought creation from the positive voltage supply to the ground through switching could be greatly decreased. In addition, in the new adder circuits, the new input signaling, which leads to a much quicker transition in its output values, immediately simulates all inner gate terminals. This enables a greater sum and carries to be used for the electricity demand of the next buffer stages. A nanometer is 1 billionth of a meter in length, or 10 times the diameter of a hydrogen atom. For this multiplier design, we opted for 45 nm technology because of its many advantages, which indulge improved microprocessor capacity, reduced voltage, transistor sizes drop, or considerable area reduction in integrated circuit occur. Upgraded panels for electronic devices, decreased power usage in electronic circuits, and nanolithography is utilized for the production of semiconductors. Input specifications and other parameters given to or implied by 45 nanometer CMOS technology are shown in below table. This table shows the comparative analysis of transistors utilized in certain combinational logic functions and their respective delays of conventional CMOS multiplier. GDI based multiplier, CMOS multiplier, and our proposed 60 full adder and 2 DXOR based 4x4 multiplier. The area and power delay product all of our design 4x4 multiplier are low as compared to the architecture presented in 5. The power dissipation, clock supplies, width length, and load capacitance presented in 4 are also quite higher than our proposed multiplier. This graph shows the 4x4 multiplier in GDI versus CMOS versus proposed multiplier. For testing purposes, we gave different input combinations to verify 4x4 multiplication. Different stages of the multiplication when 1111 is multiplied with 1111 are shown below. This figure shows the proposed schematic of 4x4 multiplier. This figure displays the complete pin names, pin states, and on-off status, which is given as input x3, x2, x1, x0 is equal to 1111 and y3, y2, y1, y0 is equal to 1111. This figure shows the timing diagram or complete waveforms of input and output. This figure shows the IC layout of proposed 4x4 multiplier. Conclusion. In this work, we present an approach for building a low voltage pass-throughout multiplier utilizing a full adder with the fewest transistor possible, that is 6 transistor and 4 transistor. Multiplier circuits are widely utilized in integrated circuits. As a result, high speed functioning of the subunits is required. A 4-bit cross 4-bit multiplier is constructed in this paper using only fundamental combinational circuits with minimum number of transistors, and its functionality is evaluated and contrasted to related multipliers assembled utilizing pure combinational architectures that were accessible in the literary works. The proposed technique results in less kilowatt area, increased performance, and low voltage multiplier architecture. Simulation findings show that the suggested approach outperforms the standard multiplier. Below are the references. That's the end of my presentation. Thank you.